All right, folks, let's solve our very first ordinary differential equation. A differential equation is really just an equation that involves one or more derivatives. So here we have the equation y prime equals x squared over y. So we have the derivative of y is equal to x squared over y. And we want to solve for y in terms of x. We want to get an explicit equation here. So what do we do here? Well, we can recognize that this is in the simplest form here. The simplest form of an ordinary differential equation is what we call separable. Now, why do we call it separable? Because we can literally just separate all the y components on one side and the x components on the other side. And then we can solve for y in terms of x. So what do we have right here? We have y prime equal to x squared over y. So right now, this is not in the form we wanted. We have y on the left side and we have y on the right side. So in order to get y's on one side and x's all on the other side, we're going to multiply each side of this equation by y. So that'll leave us with y times y prime on the left is equal to x squared on the right. Now, we want to get this in a better form here, like using the Leibniz notation. Right now, we're just using the prime notation. Either form works. It's really a personal preference, but if we use the Leibniz notation, you'll see how much easier it is. So if we rewrite this as y dy dx equal to x squared. So what did I do here? Well, I just simply replaced y prime with dy dx. And that's just easier to do the algebra that way. Nothing really changed. They're the exact same equation, but it's just simpler. And why is it simpler? Well, we notice we have a dy dx on the left-hand side here. So what we could do is we could multiply both sides by dx, and we'll get this. We'll get y dy is equal to x squared dx. Now, can you actually multiply by dx? Yes and no. I'll make a separate video of that next and kind of explain why we can do this. The short answer is yes, you can do this, but it's not the same exact thing as multiplication. But you can do this. You can do this where you essentially multiply both sides by dx, and we're going to have it separated out this way. So now we have y dy is equal to x squared dx. And, we're almost there. All we need to do is integrate both sides. So if we integrate y dy equal to the integral x squared dx. So if we go ahead and take this integral, these are pretty simple integrals. We just get y squared over 2 plus some constant is equal to x cubed over 3, also plus some constant. Now, these are different constants, but we can basically just combine the constants. Because at the end of the equation here, we don't really care what the constant is. And you'll see what I mean at the end here. So we can just combine these. We can get y squared over 2 is equal to x cubed over 3 plus some constant. Now, all I did is I just replaced this constant here with these two basically added together, or this one with this one subtracted. And we'll see why that works at the end. Now we're almost done. We need to multiply both sides by 2. So we'll get y squared is equal to 2/3 x cubed. And again, we can multiply this constant by 2, but since it's a constant, we don't really care about the value. We can just leave it as the constant still. And so now all we have to do is take the square root of y. So we're going to get square root of y squared. So we're going to get y is equal to plus or minus the square roots of 2/3 x cubed plus some constant c. So that's the final form here. We solved the differential equation. So practice exercise you can do on your own is actually plug this whole equation in to this original equation, and you'll see that it works. You can plug it in here for y, and you should be able to evaluate it and confirm that this works. But again, going back to this constant here, the constant doesn't really matter here because it's just the constant value that we use when we're basically taking the integral. So if you remember back from your earlier calculus courses, whenever you take an integral, you're going to get a constant. But we don't care about the constant now. We will care about the constant in a few videos when we start going over initial value problems. Once you have initial value problems, like say y of 0 is equal to 1 and y of 1 is equal to 2 or blah, 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 then you can go ahead and solve for the constant. But for right now, we'll go ahead and ignore that. We didn't give any initial value problems, so we don't really care what the constant value is, but we just want to know that the constant is there and it exists.